Tiga.
Assalamualaikum and good morning, everyone. Today we are going to do group presentations of assignment 1, which is shaft and related components. So before we go to any further, I will introduce ourselves first. We are from group 9 of EMM 3507 Engineering 1. The presentators is including Alif Hakimi, Nur Najiha, Nur Ashikinso, Nur Fahana, and also Siti Aisha. Next. So the topic will be covered for today is the material for shaft and also the shaft design for torsional compression loading. Next will be explained by Ali Fakimi.
So, Assalamualaikum and good evening, everyone. So for the introduction is my part. So shaft is defined as the long member of round cross-section that rotates and transmits power. It also has solid or hollow shape of circular cross-section. It also can have non-circular shape and doesn't need to rotate. For the design, it must be designed so that deflection doesn't exceed the limit. If there is excessive deflection occur, for the lateral, it will cause noise and hamper gear performance, while for the torsional, it will affect accuracy of cam or gear-driven mechanism. This is the shape of the shaft, which is solid and hollow. This is the SL. It is defined as the non-rotating member that does not carry torque but have function to support something such as wheels, gear, and so on. It is usually found in car. This is the application of shaft, which is in gear, in the pulley, in the flywheel, crankshaft, and in the sprocket. So it can be said that shaft is really important in our industry. That's all from me.
Okay, so I will continue. For the next part is the design of shaft. Okay, so I will touch the part that Ali Hakimi not touch before. So the shaft basically have a coupling that are used to transmit power, in which from drive shaft, which is such as motor, to a driven shaft, for example, gearbox or wheels. Machine elements such as gears, pulley, flywheel, sprocket, and clutches are mounted onto the shaft. So they will be used press fit, key, dowel, spin, and spinner to attach those machine elements that I have mentioned. So the shaft will rotate on rolling contact bearings or bush bearing. Last but not least, retaining ring, truss bearing, grooves, and steps in the shaft are used to take up Asia load and locate rotating element. So next. Okay, so basically this is how the shaft will be connected from a driven shaft and a drive shaft. So you can see there is the coupling, bearing, driven machine and motor that I have mentioned in the previous slides. So that's all for my part for now. So we'll pass for the next presenter.
So it is my part also, the shaft of materials. So basically, deflection is not affected by strength, but the stiffness, which is defined as the modulus of elasticity. Modulus of elasticity is essentially constant for all steel. As example, when car is when a car is going down into the hole, it will have deflection of the front axle. So this is one of the example of deflection occur. Strength of the materials need to support the load will have effects on the heat treatment and choice of material. Low carbon, cordon, or hot rolled steel such as AISI 1020 until 1050 are the most common materials for shaft. So this is the fatigue failure of shaft. Sometimes shaft also can have fatigue failure, and it can be reduced with the increase the strength of materials. But at a certain level, it will have fatigue failure on the notch limit, and it will counteract the benefits of higher strength. As example, if even we use the higher strength of shaft, higher material strength of shaft, it if the shaft have a notch, it it still can have fatigue failure, and it will begin at fatigue failure. It will begin at the notch, and it will propagates to the another section of area and break and will damage the shaft. So this is the example of fatigue failure in shaft. The first photo is happened due to overloaded by torsional stress, while for the second image happened due to the motor that suddenly stop running. The another one is the another fatigue failure example of shaft. So for choosing a suitable material for shaft, we start with a low carbon steel and cheap for the initial design calculation. If the lower one already can support the needed load, just proceed to the next stage. While if the lower one cannot support the needed load, just increase to we need to increase to higher strength. For example, we we still can use the higher strength of shaft, but if the lower one can already support the needed load, just go on with the lower one because it can save more money. So for the cost of material, uh, by considering the budget, choose the material with lower strength and bigger in diameter. If the budget is not a problem, just go for a higher strength and smaller in diameter. Typical alloy steels for heat treatment is ANSI 1340-50, 3140-50, 4140, 4340, 5140, and 8650. So for the surface hardening of shaft, basically shaft is shaft is doesn't need to have surface hardening, but it is in special case for the bearing surface because bearing surface will have to expose to dirt, sand, water, and so on. Typical material choice for surface hardening include carbonizing grades of ANSI 1020, 4020, 4820, and 8620. For the machining cold round shaft, basically in the market, we can have cold round steel with the maximum diameter of 3 inch. In the project, if we just need a just need a bar that can have such as 1.5 inch or 2.0, we can have machining process. It is different from hot rolled steel because all the part need to be machined all over, while for the cold rolled steel it is can left unmachined areas such that do not require fitting of component. Fitting of component is the area that need to be attached to components such as crankshaft, wheel, gears, and so on. So for the concentricity vector, when measuring the shaft, the more residual stress is required, and it will cause warping. If concentricity is important, it may be necessary to rough machine. Then we need to remove residual stress and increase strength, then finish machine dimension. So this is the normal shaft, and it is after have warping effect. This is the production of shaft. Basically, we use CNC machine because it is more precise, and but it is quite expensive compared to manual machine. We can make shaft smaller and produce polished surface. For production of shaft, uh, for the production of shaft, turning is the usual primary shaping process. It is also can reduce more budget by removing the less material. While for the high production, we need to have a volume conservative shaping method such as hot or cold forming or casting. And minimum material in the shaft can become a design goal. For this type of high production, the material chosen is cast iron. While for the properties of the shaft locally depend on its history, such as cold work, cold forming, rolling of fillet future heat treatment, including quenching medium, agitation, tempering regimen. For this type of properties, stainless steel should be considered. That's all from me.
Okay, or explained when the shaft is subjected to an axial load of F, in addition to torsion and also the bending load, such as in propeller shaft or ships and shaft for driving the worm's gear, then the stress due to axial load must be added to the bending stress. So this is the bending equations where the equation is equal to the bending moments over moments of inertia is equal to the bending stress over the distance from the natural axis. So we rearrange the equation so we can get that 32 m over pi d cube, where d is the diameter. So next. So this is the stress due to axial loads. For the solid shaft, the stress is equal to 4F over pi d square. And for hollow shaft, the stress is equal to 4F over pi square bracket in square outer diameter squared minus the inner diameter. So the K stand for the ratio of the inner diameter to the outer diameter, which is equal to F over pi d outer diameter squared in bracket 1 minus k squared. Next. The resultant stress, which is in tensile or compressions for solid shaft, is equal to 32 over pi d cubed in bracket m plus fd over h. And by substituting m1 is equal to m plus fd over h, we can get that the resultant stress is equal to 32 m1 over pi d cubed. Next will be explained by Siti Aisyah.
Okay, so this is the resultant stress for hollow shaft. So this is the basic yield stress. So when we rearrange the equation, so we will get the final resultant stress for hollow shaft, which is yield stress equal to 32 bending moment over pi inner diameter cube times with 1 minus k power of 4 brackets. Okay, next. Yeah, so this is the column factor. If cylinder shafts are subjected to compressive loads, column factor alpha must be considered to take the column effect into account. So bending stress given by it depend on what shape of the shaft have. So the first is the solid shaft. So the bending stress is as given in the slide, and for the hollow shaft, the bending stress equal to alpha times 4f minus pi inner diameter squared times with bracket 1 minus k squared brackets. Next. Okay, so this is the column factor. So it depends on the cylinders ratio, which is L over K. So if the cylinders ratio is less than 115, so the column factor is as given 1 over 1 minus 0.0044 times with cylinders factor. But if the cylinders factor is more than 115, so the column factor will be U stress times cylinders factor squared over constant pi squared Young modulus. So the constant it depends on the column condition. So the constant it can be divided into three types. First is the both end hinge. So the constant will be 1. So for the fixed end, the constant will be 2.25, and for the both end pin, the constant will be 1.6. Next.
So I will explain about the twisting and bending moment. So for a solid shaft subjected to fluctuating torsional and bending load along with an axial load, the twisting and bending moment is given by these equations. So it will end up the twisting moment equal to pi over 16 multiplied by shear strength and diameter cube. So for the bending moment, it will be equal to pi over 32 sigma c and d cube. So if no axial load is applied on the shaft, so if F equal to 0, and if the shaft have axial tensile load, the column factor will be equal to 1. So next. So for hollow shaft, the equation is exactly almost exactly the same with the solid shaft, but except with the ratio of inner diameter to outer diameter. So for the hollow shaft, the twisting moment will be equal to pi over 16 multiplied by shear strength, outer diameter cube, and 1 minus k power of 4. For the bending moment, it will be equal to pi over 32 sigma c outer diameter cube and 1 minus k power of 4. So in this equation, the factors of Km and Kt are used to account for the natural load. Km stands for combined shock and fatigue factor for bending, while Kt is combined shock and fatigue factor for torsion. So this the table at the right side of the slide is shown the recommended value for Km and, Km and Kt depends on the types of shaft and load applied. So next. So this is just the revision. So shear strength is used in the twisting and bending moment. So for solid shaft, shear strength equal to 16 multiplies by torsional moment over pi and d cube. So for hollow shaft, the shear strength will be equal to 16 torsional moment multiplied by outer diameter over pi outer diameter power of 4 minus inner diameter power of 4. So next will be explained by GR.
Okay, this is the last part of the presentation. I will explain about design of shaft on basic rigidity. So basic rigidity is divided into two parts, which is lateral rigidity and also torsional rigidity. So the first, I will explain about the lateral rigidity. Okay, basically lateral rigidity is important in case of transmission of shaft staying and shaft running at high speed. Some lateral deflection can cause huge out of balance force, and it also important in maintaining proper bearing clearances and for correct gear teeth alignment. If shaft has a variable cross section, then the lateral deflection may be determined by below equation, and if the shaft has a fixed or the same uniform cross section, then it will be obtained by deflection formula from strength material. So the next part is torsional rigidity. Okay, torsional rigidity is important in camshaft of internal combustion engine where timing valve will be affected. Okay, the permissible amount of twist is have to less than 0.25 degree per meter length of the shaft. For line shaft, the deflection is have to be like 2.5 to 3 degree per meter length may be used as a limiting value. The widely use of deflection of shaft is limited to 1 degree in length, equivalent to 20 times of the diameter of the shaft itself. So next. Okay, so for the torsional deflection, it can be obtained by below equation, which is T over J equal to G theta over L, or it can be obtained, or in other words, deflection or torsional deflection equal to T times with L over J over J times G. So below there is the description of each alphabet that being in the equation. So for the J is a polar moment of inertia. It divided into two parts, which is for the solid shaft and the hollow shaft. So it's clearly stated which equation that can be used for solid shaft and for hollow shaft. So I think that's all for us. Thank you very much.
Thank you.